Okay. I'm comfortable to stay here. I would like to stay here. Okay, as you know from the program, the next speaker is Luca Spogli. But I'm wearing my glasses in an official way. I'm going to introduce. So Luca is a researcher at INGV, as you know. He's interested in ionospheric physics, in data analysis and treatment techniques, and ionospheric modeling, with particular regard to ionospheric irregularities scintillation. He participated or is participating to many research projects in the field of solar-terrestrial relationship and space weather studies funded by national and international agencies. He's also involved in the Pegasus Consortium, in charge of providing a space weather service to ICAO, and is advisory to the Italian member of the ICAO panel for space weather. He's the current president of the European Space Weather and Space Climate Association, and above all, is a very, very good friend of ours. So, Luca, the floor is yours.
Thank you, Michela, for the introduction. So I go back to the first day, so mainly to what Yuri showed, and I'm trying to give some more details. In particular, that's the title of the presentation. So in theory, we should, sorry, too fast. So in theory, we should address those three things. So ground-based GNSS receiver, easy. Ionospheric scintillation, not that easy. Climatological modeling, I try to say something about it. So ground-based GNSS receivers. What we learned from this day is that it's faster than me. What we learned from this day is that GNSS signals pass through the whole ionosphere. They start 20,000 kilometers above our head. They pass through all the ionospheric layer. They are received at ground, and they provide an integrated information. So what we can do is we can squeeze the information experienced by the GNSS in the several layers of the ionosphere into a flat ionosphere. Okay, this will bring some assumption, and we must take care of this. The other important thing, the other message to remember, is that the ionospheric effects is the main source of error in the positioning application, in the positioning that GNSS are supposed to provide, besides other effects. So what we can get with GNSS observations. So mainly we can measure the pseudo range of the phase. At a certain level, we can measure those two things. And the satellites, again, pass through all those errors. And this is the ionospheric information that counts into the determination of the pseudo range and phases. So the fact that electromagnetic waves emitted by GNSS satellites are not passing into a vacuum, but in the ionosphere, translates into two things: a delay of the modulation and an advance of the carrier phase. That is somehow good, because we can do some work on the two frequencies emitted by satellite and retrieve some information about the medium that is in between the satellites and the Earth. Okay? So there are usually the receivers are able to record all the frequencies emitted by the satellites, that are at least two. In most of the cases, at least, they are three. And for instance, we can, if we combine two frequency in the so-called geometry-free observation, you can derive the amount of electron, the integrated quantity of electron you have along the ray path. It is the TC, the total electron content, and this is the formula. In this epsilon, there is a word of techniques and method to account for this for this epsilon. I'm not going to the detail of this, but there's several people working on this epsilon. Some of them are here, seated here. So, and you can also try to make a thin shell of the ionosphere, so squeeze the information and report everything at a single ionospheric layer. That is really a strong assumption, but you can't do anything else, okay? Then you can try to observe those TC along the ray paths. And then if you try to follow those TC values of a supposed smooth ionosphere, this is not true at all, because if you calculate the variation along an arc, that's what's called rate of TC. So the variation over the arc, over 2 instants of time, you start seeing things like this. So there are variations that are not smooth at all. So there is something in between. Okay, so is this scintillation? Wait, let's wait a little. Before start speaking about scintillation, we should learn a little bit of history of scintillation. There are 3 categories of scintillation. One is the interplanetary scintillation, one is the tropospheric scintillation, and one is the ionospheric scintillation, our beloved ionospheric scintillation. These are caused by inhomogeneities, the solar wind, neutral turbulence, and ionospheric irregularities. That's the words I would like you to remember. And the effect is that fluctuation of the intensity of radio stars, fluctuation of the optical ray paths, the twinkling of the stars, fluctuation of the amplitude and phase of the signal. So the keyword is fluctuations. So what we are looking at is fluctuation, a fluctuation of something, amplitude and phase of the signal. Okay, so we are looking for something that is exactly the twinkling of a star. But this will bring some complication because the picture is not easy as it seems. So before considering scintillation, let's have a look at the cause, so at the ionospheric irregularities. So Yuri nicely, in his nice presentation, introduced a lot of the irregular behavior of the ionosphere, and it's good because you saved a lot of work for me. So in a slide, one can squeeze all this information about irregularities in terms of scales. Okay, usually by studying irregularities, one should think in terms of scales of the irregularities, and the ionosphere is so largely varying in space and time that you can go from the small scales, so from the meter or even centimeter level, up to the 100 kilometer scales. You can go into a small scale, into a plasma bubble. You can go in the mesoscale. For instance, I stole this slide from your talk, Yuri, actually. So there are medium scale ranging from about kilometers or few kilometers, and there are the large scale, which is the general, the overall, the large scale ionosphere. And now the complications arise. So small scales are usually, of course, I forgot to mention, I'm thinking in terms of the GNSS perspective. So these are small, medium, and large for L-band signals. Okay, if you go to VHF, UHF, HF, of course, small, medium, and large can change. So we are thinking from a GNSS perspective. So small scales for L-band signals means below the Fresnel scale for L-band signals and the geometry of observation of GNSS received at ground. And this means kind of 300, 400 meters. This is the reason why the red is slightly above 100 meters. So when you are able to detect small-scale irregularities, mainly because there is a growth and decay of instabilities. Okay, these are the main, or not the only one, but the main processes leading to small-scale instability processes. So shear-driven instability, so growth and decay of the instabilities in the high latitude, mainly due to Kelman-Kelvin and gradient drift instabilities that are very rare, and Rayleigh-Taylor instability on low lectors that are conversely very common. Let's go to the medium scale. Medium scale, they are mostly storm time phenomena. Mostly storm time phenomena induce medium scale. So auroral precipitation, polar cap patches, auroral blobs, tongues of ionization, ionospheric trough, storm mass densities. These are these are storm time phenomena, mainly affecting the high latitude of the ionosphere. And there is again equatorial plasma bubble that are not storm time phenomena, and they have medium scale irregularity embedded into it. And then there is the large scale. So this nice picture with the ionosphere I've seen from the sun, I would say, from the moon. Okay. So these irregularities, these scales of irregularities translates into probably the most known, the most famous picture of the irregularities climatology. We are talking about climatology. So this is the first thing you have to keep in mind. This is a very famous picture from a very known colleague that passed away in the last decade, Paul Kintner. And this is frequent or infrequency, the frequency or infrequency of irregularities, so of scintillation. Okay, so this was almost, I hope, known for everybody. So we can start to go in the details of scintillation. So let's start. Remember that we started from fluctuation, but we speak about scintillation. These are not exactly the same thing. I will show you. So let's start from how we measure those things. So we need to measure some fluctuations, okay? So we need a GNSS receivers, and usually scintillation is a fast phenomenon. So you need to sample your signal quite fast, usually 50 to 100 hertz. Is this enough to study scintillation? No. A scintillation receiver is not because of the sampling frequency. What makes a scintillation receiver are those things. You need low noise. Phase noise phase must be measured carefully. So you need low noise and stable clocks. And this is for scintillation part. If you need to monitor, that is another keyword in these ISMRs, you need a firmware that is able to calculate the scintillation indices. I'm going to introduce something that quantify the oscillations, usually on a 1 minute basis, historically on a 1 minute basis. This is not suitable for many applications at high latitude. And you need, as a monitor, an output in real time or quasi-real time. Okay. So this is for every receiver of the new generation, multi-frequency and multi-constellation, it's obvious. This is just for scintillation receiver. These make the scintillation receiver costly with respect to the traditional geodetic receiver. So 1,000 with respect to 20,000 euros. These are generations of scintillation receivers, so the GSB 404, early 20s, late 90s, the Polar XS, early 2010s. In the middle, there is the GPS version 6, so they are both Novatel, and now the top is mostly the Polar X5S from September. Okay. How to measure a fluctuation? Fluctuation is a variation, so you can use a statistical index. You can measure the standard deviation of the amplitude and the phase. Okay. Over a given interval, typically 1 minute, because it's the time that traditionally it's able to account for the scintillation variation. And you can measure the standard deviation of the normalized signal intensity, and you can measure the standard deviation of the T-trend phase. This word is in red because the trend is the real problem of phase scintillation. Okay. So you have, this is an example, you have raw amplitudes like this. You calculate those indices and you translate this information into something like this. I don't count for this. This is the problem with this is not good, but you can translate this into this. Okay. Is everything clear up now? Okay. So the simplified picture. So basically, you have your satellite moving across the ionosphere. There is an irregularity a medium scale irregularity with small scale irregularities embedded into it, typically elongated in altitude and on the horizontal plane. Then you move, you start having a slight deviation because there is the variation of the refractive index of the ionosphere. You start to get oscillation. Then you start having, you are in the middle of the mess, you start having multiple scattering, diffraction effect, and then slowly you can get out. And of course, there are many satellites in view. And in general, this can reduce the accuracy of positioning and the loss of log. Okay? This is a simplified picture. So this is the typical scintillation time profile one can get from traditional ISMR receiver. So this is a receiver we have INGV manages in Antarctica. It's here in the Concordia basis on the Antarctic plateau. This is the field of view. These are the auroral orbital boundaries, modeled, quiet, and disturbed. So this is well into the polar cap. And this is the September 2017 storm. This is 8 September in particular. And as you can see, there is some amplitude and phase scintillation indices, and there are variation over time. Each color is a different satellite. So there are some variation occurring here, and you can see here there are differences between S4 and amplitude scintillation. Okay, so for instance, in my life, I have seen hundreds, thousands of those time profiles to understand. Okay, why we use this index? For several reasons. Index are actually very nice for engineers, but they are not a physical quantity, but they are useful to provide some information. For instance, the impact of increased scintillation indices often translate into increased probability of losing the lock with a given satellite. So for instance, here there is the probability of loss of lock as a function of the value of this sigma phi. Sigma phi, it's the trend here with a Butterworth filter at 0.1 Hertz cutoff. It means that you need to detrend your phase because there is the Doppler of the satellite, and you need to remove it somehow. Okay, so the standard way is 0.1 Hertz. If you want, during the coffee break or during the lunch, I will tell you the story of this magic number, 0.1 Hertz. Okay. I have a tattoo with 0.1 Hertz on my left arm. No, I'm joking. It's not true. Okay, this is high latitude. This is low latitude. This is the scintillation probability and the cycle slip slot probabilities at low latitudes for three constellations, and they match quite nicely. So higher scintillation values, high probability of loss of log. But scintillation affects positioning directly, not just through tracking. Okay, I don't know if you are able to catch the difference, but tracking it means that you lose your satellite. Positioning means that the signal is so feeble, so weak that you cannot do position. Okay, so this is an example from a work from the Norwegian colleagues. This is phase scintillation index in the 0.1 Hertz way of conceiving it. This is Roti index that you have learned a lot about from Yuri, and this is the positioning error from with two positioning techniques, RTK and PPP, and you see there is enhancement of the errors in correspondence with the enhancement of those indices. And again, this is an example of distribution of positioning error. This is over Hong Kong, so it's low latitude. When you have no scintillation, and scintillation, of course, when you have scintillation, there is the error spread out. Okay, perfect. So higher values of scintillation index means higher probability of tracking error and positioning errors. That's fine. Okay, but let's have a deeper look. What causes fluctuations in the GNSS signal? Two mechanisms. One is refraction. Okay, so there is a variation of the refractive index in the ionosphere. It causes fluctuation of the signal. The problem is that it affects the full spectrum of irregularities because every scale size means a variation in the refractive index in the ionosphere. So it's flat. all over the scales, okay? And it affects just the phase. Amplitude is untouched from refraction, okay? The physical mechanism causing the fluctuation is the phase mixing. And this causes deterministic fluctuation, and I will show you more. And there are some mitigation techniques. Remember this magic word, this magic sentence, ionosphere free linear combination. That is another combination of the two possible signals emitted by the GNSS satellites, and it causes a positioning issues like psychoslips, loss of lock, phase noise, and second-order ionospheric effects that are effects at the order of the centimeter, a fraction of centimeter. But there is another problem. There is diffraction. Diffraction is due to the fact that irregularities of the small scale below the Fresnel scale act as new wave source. And this creates the correlation and interference of the signal recorded at ground. And the effect is not deterministic at all. It's stochastic, and it's a problem because you cannot simply apply a combination of frequencies to get rid of this. You need to make something more robust, more not so easy. Maybe the most easiest thing is to deweight your satellite, but in some occasions it doesn't work at all. So please remember those two mechanisms. A deeper look. So this is the amplitude of a signal, the spectrum of the amplitude of a signal. It behaves like this. There is a flat spectrum and then a slope like this. This is diffraction. This is the diffraction regime. And this breakdown is exactly the Fresnel's frequency corresponding to the Fresnel scale. Okay. I don't demonstrate this, but the S4 index is proportional to the integral of this spectrum in all the frequency range. This is the Nyquist frequency, for instance, if we work with 15 Hz, it's 25 Hz. Okay. So this is the Fresnel frequency. The Fresnel frequency is proportional to the relative velocity between the ionosphere and the ray path. Okay. So it depends on the velocity. And it depends on the Fresnel scale. The Fresnel scale depends on the square root of 2 lambda, the wavelength, so 19 centimeters for L-band signal, and the h of the IPP. So you can assume that it's a single layer ionosphere, and so you have a geometry of observation, the altitude at which you get the diffraction. Okay, great. And that's the refraction. There is refraction. Again, it's flat. So it covers all the frequency ranges. And there is a problem here. Because oops, sorry. Okay. So below this frequency, theoretically, there is purely refraction on your face. Above this, there is a mix of two effects because the diffraction affects both phase and amplitude. So here you have a mixing. So there are two regions. Here you have only refraction on your phase. Here you have diffraction on your amplitude, and refraction plus diffraction on your phase. But you have to determine your phase. Where do you like? Where would you prefer to have your cutoff frequency if you want to have a reliable sigma file? Do you have any guess? Consider that there is a magic number, 0.1 Hz. So 0.1 Hz can be everywhere. Okay. So if you put 0.1 Hz here, there is some refraction. Let's imagine that you put here. So you have bulk of the refraction cut out, a part of your sigma feed that contains purely refraction, and a part that contains a mix of refraction and diffraction. So in theory, what you can do, for instance, if you set 0.1 Hz, you have this kind of intermediate. So ideally, if you want to get rid of the bulk of the refraction, and why? I will tell you why. Maybe you should move close to the Fresnel frequency, because at least you have the bulk of the refraction cut out. Okay, and you know what's in your signal. Okay, that's fine. That's the problem, because the Fresnel frequency depends on the relative velocity between ionosphere and rainbow. And this magic number, 0.1 Hertz, comes from wideband experiments in the 80s or early testing of scintillation receiver at low latitudes. And the plasma at low latitudes is 1 order of magnitude lower than the plasma at high latitudes. So this magic number is not suitable at all, because you are putting together a lot of refraction that maybe is not the real problem, because it's deterministic. And I'm going to show you. So I have, okay, question time. This is a L1, the trended phase, okay? The trended in, and a question for you. Would you call it scintillation? Why not? Are you able to tell if it's scintillation or not? Why? Okay, I help you. I give you also L2. If you calculate sigma phi from this, will you get enhanced sigma phi or not? It's the standard deviation of the phase of a given interval. So I will get some sigma phi enhancement there. This is not scintillation. Why? Because if I use remember the magic sentence, ionosphere-free linear combination. So if you mix those two frequencies in a nice way, da-da! There is no scintillation at all. You are just not removing all the refraction here and here that affects the two phases. But if you make the ionosphere free, so if you cancel the ionosphere, there are scintillation. These are phase fluctuations. This is not scintillation, because it's deterministic. You can cancel by simply composing the two frequencies. What about this? You can't tell. You can't tell as soon as you don't see this. The ionosphere free linear combination. Now there is something here. This is scintillation, because ionosphere free linear combination has a residual oscillation that you cannot cancel out by simply removing the first order ionosphere. Fantastic. So if you wisely detrend your signal, if you wisely select your cutoff frequency in order to have a sigma phi that contains the diffraction and just the minimum amount of refraction you can't get rid of, because it covers the full spectrum, you will see things like this. So the S4 is the blue for this event, okay? And as you can see, the red and blue, the red and black are calculated with two different approaches of calculating the cutoff frequencies, but in a smart way. See the shape, and you will see the scatter. If you see the scatter plot, the correlation factor is practically 1. They are behaving exactly in the same way, because it's exactly the same phenomenon, plus a glimpse of refraction in the same indices. Okay, I cannot go into all the details of what does it mean philosophically on the use of sigma phi. But the main message is, don't use sigma phi in the standard way, but you have to know what you are having in your index. By the way, so if you calculate your cutoff frequency as a function of time, you can also calculate, remember, the relative velocity between the ionosphere and ray path. So black is the cutoff frequency. Orange is the relative velocity. This is high latitude. This is, again, Concordia Station, Antarctica. Look at the range. The range of the velocity calculated with this technique is between 550 and 200 meters per second. It's a reasonable plasma dynamics velocity for high latitude ionosphere. It can be even larger. This is, again, September 2017 store. This is a measurement with 3 different independent techniques of the irregularity in the low latitude ionosphere in the post-sunset hours. So this is the plasma bubbles dynamics. look at this is a statistical work made on 6 months of data. So the values are way smaller. And this is the reason why 0.1 Hertz cutoff is not that bad. Okay, you must do the same, but it's not that bad. And you will see remember the time profile I've seen before, I've shown you before. There were a lot of sigma phi events and poor S4 events. This is not true. They were exactly the same events. The other ones, the excess of sigma phi is purely refraction. Okay, this is another example in which sigma phi depends on the speed, while S4 not. This has been published 5 years ago. So this is another proof that sigma phi is a strong dependence on the plasma drift velocity. It's not reliable in a standard way. But it's provided by more scintillation monitor receiver. Okay, there is another problem while treating scintillation data. They are not clean at all. For instance, what can mimic scintillation? So there is the so-called multipath and reflection. This is a clean scintillation event. It is exactly the same you have seen before, but this is actually this. What's the difference here? Is that everything is there. Everything recorded by the scintillation receiver is there. It's a mess. You cannot use it. What you can do, usually you can cut the elevation. This is the more rough and more common approach. So you simply cut the elevation and you go back to the original, or you can do the so-called sidereal rejection, because if you have a building, the building doesn't move. So the scintillation you have because of the building will be exactly the same tomorrow. It was the same yesterday, besides 4 minutes. That is the difference between the day and the sidereal day, because in GNSS have the periodicity with the sidereal day. I will show you an example later. This is not the only problem. So if I will show this, please don't read the other things. So this is a nice work just published by Emanuele as a first author. So do you like these S4 events? That is something we have seen many of them. And when we saw this, we said, it stinks. Yes, it stinks because it's artificial interference causing S4. We have recorded in the Lampedusa island in Sicily with some seasonality that can be somehow related to some activity in the area. So we are still investigating the cause, but we reported the effect. Mitigating those kind of things, it's not easy at all. These are dirty data, hard to understand. Okay. What time is it? Just to
20 minutes.
20 minutes. That's perfect. Okay. Let's go to the bulk. So what you learned up to now, we have fluctuation and scintillation. Please don't mix it. If you mix it, you will get back to 10 years ago. Okay? Don't mix it. So standard, the sigma phi is provided in a standard way by scintillation receivers. Remember that you are putting together scintillation and refraction and fluctuation due to refraction. So by comparing sigma phi and S4, you can understand what's really happening. Let's do some climatological modeling. That was also my, but we played a lot with climatological modeling in the last 15 years. So maybe some words about the climate. So the ionospheric climatology is usually the study of the ionospheric climatology addresses general, synthetic, average, and large spatial scale ionospheric features in contrast to specific ionospheric and space weather events. This is a possible definition. We tried to introduce some years ago a definition of the scintillation climatology to assess the general recurrent features of the ionospheric irregularities dynamics and temporal evolution along data series, trying to catch eventual correspondence with the scintillation occurrence. Okay? So this is just a table to show some ideas of what you can model, what you can understand with some climatological approach. So, and we really made a rough comparison between climatological models and physical models. So if you have a transient phenomena, the climatology would not model. Okay, and maybe the physical model, yes, if accounts for this specific transient phenomenon. New physics, new phenomena, yes, but only if they are not transient. And the physical model, if it's a new physical process, it's not modeled by definition. The average behavior of the physical quantity, it can be modeled by both. Phenomenon that is not in the data cannot be modeled with empirical approaches, of course, but it can model with physical model. And phenomenon not formalized in a theoretical way, it can be modeled if the data account for it. And it's not modeled if it's not modeled. Of course, quite often semi-empirical model is the solution in a rough field, of course, so mixing the two of them. This is just to give you a clear idea of the two sides of the two approaches. So, some ingredients, okay? What you need: suitable networks of ionospheric scintillation monitor the receivers. If not available, geodetic receivers offer some proxies related to the mesoscale irregularities, okay? Of course, you need a big bunch of good scintillation data. You need stable observatories, the longer the better. Data quality in selection and integration is an issue. For instance, these are the scintillation network that you can get access to with the eScience Center. Maybe I can show you a little bit of this at the end of my talk. I would like to finish, and then I will show you how to get access to those data. These are mostly owned by us or by partners that are providing the data to us. There is an ongoing project. A project just started to integrate the Canadian network of scintillation receivers into ESWA and vice versa. And there is an open discussion with the Madrigal and with the, so chain plus Alaska and other USA data. And we are trying to integrate also the NAVER, the former Cigala Calibra network, into the ISWA database. So we are aiming at having the largest scintillation receiver database all over the world. So we developed a technique that is called ground-based scintillation climatology. We've published some papers about this in the past. So it was an old idea. So some of those terms are kept because we love it. And they are part of INGV people history. So they are maps of ionospheric scintillation and TC-derived parameters in terms of mean value and standard deviation or occurrence above user-defined thresholds. Of course, mainly scintillation indices, but there are a lot of nice parameters you can get from the scintillation monitor receivers you can be interested in. Of course, you need do some climatological maps. You need to define a system of reference. So usually geographical geomagnetic coordinates, universal and magnetic local time, azimuth elevation, these are usually quite used. And you can also, we develop this also to account for different geomagnetic conditions to sort the various maps. For instance, KP, IMF, DST, phase of the solar cycle, auroral indices, whatever. Okay, it's all made by INGV. It has been developed for the main scintillation receivers. Okay. Okay, these are some selectable features where I suggest I would like just to draw your attention on the fact that you can use slant or vertical indices. Okay, and I will show you a little about this. So thresholds for scintillation occurrence. This is most likely what you want to do with scintillation. Also and usually there are 3 thresholds. They can change a little, but if you consider something above 0.1 radians or absolute or unitless for S4 as a weak moderate, and 0.25 as a moderate, and 0.7 as a strong scintillation activity thresholds. Some physical assumption: if you map, you have to assume a point on the sphere, or some point, a point on the sphere. So you need to assume that you need to squeeze your ionosphere, usually 350 kilometers. You can change it, but it's quite reasonable. Of course, if you put together several receivers, there is a problem. They can, two receivers far separated can point at the same pierce point, but they are actually covering different length paths. What you can do is to verticalize those quantities, bringing more assumptions, bringing more complexity, but at least you have a representation of your ionosphere as seen from a virtual receiver standing behind the overhead. To make this assumption of the verticalization, you need to calculate the spectral index. This is routinely calculated by ISMRs if you don't want to go with the raw data, but it's not measured by the oldest scintillation receiver. So you need to make some further assumptions. So this is exactly what I was showing before. There are some formulas under weak conditions you can assume. So it is exactly like reporting your S4 or whatever, or TC as seen from virtual receiver on the overhead. And okay, let's have a look at some results. So, for instance, you can have a look at the scintillation occurrence at low latitudes as a function of the sunspot number. Okay, this is the sunspot number is the black curve. This is from a network covering South America, the LIS network. And you can see how the scintillation is above the weak, moderate, intense threshold. And you see that the scintillation strongly depends on the solar phase cycle. And this is, of course, there is also the electrodynamics of the low ionosphere in between. But this is a climatological result, okay? And you can go below the southern crest of the equatorial anomaly in the Brazil sector. When you expect to get scintillation, you can stay in a period of high solar maximum because you learned before that that's the best way, that's the best period to catch scintillation because of plasma bubble. And you can see, yeah, I know that is under the local sunset times at ionospheric altitude. So you can do a climatological maps, months, days of the year as a function of local time. You can also nicely put the sunrise and sunset times, and you will discover with your climatology that, of course, plasma bubbles maximizes in the post-sunset hours during the during the equinoxes and the December periods. Maybe you can see some, are you able to see some strikes here? I'm going to highlight for you. That's multipath. This is some residual multipath, not accounted for by cutting the elevation angle. There is still something that you need to cut out by removing these 4 minutes advance in the occurrence map. The good thing is that if you consider a higher a threshold, for instance, for the moderate, this before was weak, the multipath effect is completely vanished. So it's in the weak to moderate range. Okay? Red line. You can do, of course, geographical maps. So this is the same period I've shown before. This is the occurrence above 0, the S4 above 0.25, and see how they nicely fit with the expected position of the minus 15 degrees magnetic latitude. And this is another example for the March-October 2015. This is the ERICA campaign we conducted in South Asia. So ionosphere exists, plasma bubble exists. That's a good news. That's a question for you, another question time. So this is again the ERICA campaign. This is the Southeast Asia. This is occurrence of S4 above 0.1. This is the period. This is the whole March 2015. It's a short period, but you can do some climatological maps. This is the occurrence. Question for you. These two maps are sorted between disturbed. The first part of the month was quiet. The second part of the month was disturbed, which is the quiet and disturbed maps. So please raise the hand. This is the disturbed or the quiet maps. Please vote. Disturbed? Who says quiet? Please raise the hand. Just 4. So who says that this is disturbed? This is quiet. These are the quiet days. These are the disturbed days. So there is scintillation inhibition. Consider that the plasma bubbles are like plants. So they need seeds to grow up. If you don't give seeds, they don't grow. And you can get electrodynamical and mechanical disturbances to the seeding processes due to the storms, induced by the storm. They are called prompt penetrating electric field. That is a prompt effect when you have the flipping of the BZ. And there is a delayed effect. They are called disturbance dynamo electric field. They are due to the cross-equatorial winds. The effect, the overall effect is that you don't have scintillation at the climatological level during the disturbed days. Let's have a look at the high latitudes. I almost finished. We installed our first receiver in Ionospheric in 2013. We were very lucky, very lucky. 2003, sorry, of course. September 2003. Maybe you can remember that in October 2003, 1 month later, there was the Halloween storm. And we are the only one in the world having scintillation data highlighted of the Halloween and November 2003 storms. This is Ionospheric. It's the perfect site to study the ionosphere. It's the perfect site. You have the cusp, you have auroral, you have the cusp, everything is there. All the highlighted ionosphere is there. You can have fun for decades as we are having. So this is the maps of sigma phi above 0.25 for different values of the cutoff frequency. Looks like this in magnetic local time and magnetic altitude adjusted corrected geomagnetic latitude. The sun, so this is 12, the sun is here. This is the nose of the magnetosphere. This is the tail of the magnetosphere. This is the cusp signature. Looks how the scintillation maps change if you change the cutoff frequency. This is S4. Can you spot the best cutoff frequency to match the two? Me not, if you can. So you cannot do the exercise of the cutoff frequency at the climatological level. You must do it minute by minute. That on raw data for climatological purposes, it's a nightmare. Okay. You can sort the maps according to the KP, for instance. This is quiet condition, minor, moderate, strong, severe, extreme condition, sigma phi above 0.25 radians, S4 above 0.25 radians. This is the standard sigma phi. This is scintillation. This is scintillation plus fluctuations. You see, the cusp signature, so the direct precipitation, the amount of particles that enhance the gradient in the cusp, they don't cause scintillation. You can see here that this change, the auroral oval changes climatologically, and then the corresponding formation of large mesoscale irregularities changes. The most intriguing thing is this. What's this? What I've said at the beginning. What are the causes of small-scale irregularities in the polar Kappa ionosphere and the highlighted ionosphere? Instability processes. This is the effect of the gradient drift instability forming when the tongue of ionization is well formed in the nighttime sector. And these are small-scale irregularities in the nighttime polar cap. Okay, these are the same maps for different phases of the solar cycle. Of course, the maximum, the solar cycle, the largest the solar maximum, the solar condition, the largest is the occurrence of sigma phi and S4. And I can show you also something like this. It's very nice, this exercise, because you can also sort according to the IMF conditions. This is an example of sigma phi greater than 0.1 for BY, positive BY. Sorry, this is, this one should be negative BY. This should be negative BY, sorry. DZ is the same BY changes. These are climatological maps derived from Superdarn in a work It has been updated, but this is from the previous work by PITHIA and all. And you can see how the convection cells changes, and this reflecting how the pre-noon and post-noon sector are favored according to the different conditions of the IMF, as reported in the convection cells. So, take-home messages, and I will show you a little bit if I have time, of course.
5 minutes.
5 minutes, that's perfect. In 5 minutes, I will show you the scintillation data in the eScience Center and on this as well. So, irregularities in the ionosphere cause on GNSS signals, phase fluctuations, and phase amplitude scintillation. I hope I convey the message that please be careful in distinguish them. They cause tracking, phase fluctuation, and positioning scintillation issues. They are routinely provided in a standard way by scintillation monitor receivers. They must be used wisely. High and low latitude ionosphere are featured by scintillation and phase fluctuation. High latitude is the more exposed to the forcing of the geospace, while low latitude plasma bubbles are quasi-regular phenomenon, but they are modulated by geospace forcing and the initial dynamics, changing the electrodynamics of the low latitude ionosphere. And some of those features can be nicely revealed by climatological model. Okay, so I take the occasion to go fast in the eScience Center. You can browse your data collections here. You will see ESWA, which stands for Electronic Space Weather Upper Atmosphere, Scintillation Indices, and Total Electron Content Database. And here you can have the link to many things with which you can interact with the ESWA web server and the ESWA portal. For instance, you can access to the RESTful API to get the scintillation data. The first thing I suggest to do is to, oh, no, not here, sorry, but this one. Second one, the overview, the near real-time data of the scintillation index and TC. That it's here. And here you can get access to the last time profiles and maps of the scintillation indices. This is, for instance, our scintillation receiver in 2-layer base in Greenland. Okay, you can also slightly change to the last 24 hours. You can change the elevation masks to account for the multipath effect, and you can also select the scintillation. If you want, you can go deeper into the, and you can get the data sets, the time series image, the IMAP image, and you can also explore the data. If you want to go back in time and get your data to cook up your climatology, you can go to the scintillation parameters explorer. For instance, if you want, you can go to one of the low latitude stations. For instance, let's go in South America. So San Miguel de Tucumán in Argentina. Let's see, this is S4 vertical. Let's use the slant. This mouse is far to be comfortable. S4 slant. You can also get the map of the S4. If I'm not wrong, vertical map. You can analyze the last 7 days. Let's investigate if there are plasma bubbles. And we just want to see GPS and Galileo. That's it. If you are lucky, if we got plasma bubble events.
Let's wait a bit.
That's 7 days. Okay. That's the map. You can zoom in. There is not that much scintillation in the last 7 days in Tucumán. Okay, because it reaches 0.25, 0.3. Okay, and you can also download this dataset in JSON format. Okay. Okay, it will take time. Okay. For instance, if you have the timestamp, the elevation, the latitude and longitude of the Pierce point at 350 kilometers, the satellite, the value of the S4 on L1, and the azimuth and elevation of the observation. If you click on the eScience Center again, and if you go to the this link, data access, you will get access to the documentation for the web service API with which you can interact with the database. And at the end of this well-documented page, there are examples and code with MATLAB and Python to directly interact with the web service. And that's it. So
thank you, Luca.
Thank you for your attention.
Some questions for Luca?
By Daniel. It's Daniel. Boris first. We can fight later.
What?
Thank you for your presentation. I actually have 2 questions.
Wow.
The first one, if you can please come back on your presentation on statistical results of scintillation in lower latitudes in Brazil for 2015, I guess, this period. Before you have this map, yeah, and you also have, yes. And I have here is a question. So the growth of the color on the right, it's because of the
occurrence.
Yeah, it's occurrence of equatorial post-sunset.
Post-sunset.
However, we have some occurrence before sunrise, right?
Yeah, okay. So
my question is,
you mean this, for instance?
No, I mean on the
You mean this one?
Yeah.
Okay. Yes.
So
you want to know why?
The question is, yeah, plasma bubbles post-sunset not heavily related to geomagnetic activity. However, before sunrise, plasma bubbles, are they heavily related to geomagnetic activity?
There are 2 reasons why you can get plasma bubble signatures here. The plasma bubble has been lately generated, and there are some conditions, or it was generated far away and it drifted into your field of view at later time because it takes time, of course. And of course, and usually they are referred to drifting plasma bubble or freshly generated plasma bubble, and they causes this elongation until the morning time. The bulk of these are generated in another geomagnetic sector, and they are drifting in your sector.
Thank you. And the second question, so for plasma bubbles, we're not only using scintillation indexes, but also ROTI. And why we see on the ROTI the plasma bubble structure is because they're characterized by the
high... I can ask this. You reply after my talk. So please don't tell that ROTI is a proxy for S4.
Yeah. No, I don't mean
ROTI is phase.
It's another index to use.
It's another index to use, and it detects mesoscale irregularities. It's a proxy because when you get mesoscale irregularities in the plasma bubble, you can bet you can get the small scales too. We just published a paper on space weather. It was nice because we were so lucky. Maybe you know that the Swarm constellation for some period was kept in the so-called overfly. So the A and C were separated, they put just 2 seconds separated, and the swarm B passed exactly on the opposite, higher latitude, the opposite direction. And there was a nice crossing into a plasma bubble, a single plasma bubble, just one. There are many of these, but they are in other sector, they were not covered. Okay, it was so nice because you can see that ROTI and S4 are not the same. If you because if you go down to the smaller scale, you get S4 before you get ROTI. Ideally, you can see before, if you pass in the right geometry, you can see ROTIs enhancing before and then S4. Okay, and yes, mostly this.
Okay, because my question was,
Sorry.
yeah, for the ROTI, it's because we see high gradients, and in other space where the event that can create such gradient, it's solar flares. And can we see
Solar flares with those?
With the scintillation indexes?
No, but you can see TC variation in the range time means. So consider that there is a nice paper, maybe from Bruce Sultani, about the 2003 Halloween storm, in which you can see the TC variation that have a peak in the subsolar point and they slowly decrease by going up. And we also have seen this in the X9.3 during the September 2017 storm over Italy. Getting back to the S4 and ROTI, there is a nice paper from Charlie Carrano that tried to match S4 and ROTI. It's nice. The only problem. If you want to rescale your ROTI to S4, you need to know the effective velocity. So you need an external estimation of the effective velocity. Then you can measure. Because let's remember that S4 doesn't have any relation with the dynamics. It's purely Fresnel. Large scale, sigma phi, ROTI, phase variation have the problem of the dynamics of the plasma. So if you want to rescale S4, ROTI is a good proxy of S4, provided that you know the velocity of the ionosphere.
Thank you very much.
You're welcome.
We are already late, so quick question. Last one.
Daniel.
Thank you, Luca, for your lecture. Just a quick one in this same diagram. Where you show the 4-minute structures.
Yes.
Yeah. So how do you normally count or do this? Do you just remove or you check and
you can do it, of course. You can check longer data series. You can do climatologically, or you can simply do. No, sorry, in the wrong computer. You can simply do like this. You don't have multipath anymore.
Okay,
you simply check the threshold of scintillation occurrence. Now, of course, it depends on the application, Daniel.
Okay.
Consider that if you deal with TC data, multipath, it's not a big issue. It's not a big,
No, it's for scintillation data. The S4.
If we have scintillation, I don't know if I can calculate TC from GNSS. You can calculate TC only if you are in a purely refractive environment. If you have a diffraction, I don't know.
Okay.
That's not the geometry free. It's not TC in that case, but I don't know what's that in that case.
Okay, thank you. The data in the eScience, is it treated like this or it's the raw data?
No, you have to treat it like this.
Okay.
That's shown that. Just if quick, otherwise we can discuss.
Yeah, I'm just surprised you're a 30-degree cutoff. So do you not have a station selection? Because geodetic receivers, which by the way also cost 20K, geodetic receivers, we place them on spots where there is like minimum multipath, or we put them on a mask, and we have a choke ring. Do you use choke rings?
Of course.
So how can you? I don't understand how you can have such big multipath effects. We don't have them.
maybe if you've seen it like this, maybe you have it in any case.
Anyways, you are not always so likely to have a flat area around you. Sometimes there is just one single building that can make you.
Now, consider that okay, to better reply to your questions. These are very small effects that you can see by looking in a specific range of the amplitude variations. I don't think that these affect the positioning. Okay, and for sure, okay, in most of the places you can decide where to put your antenna, your mast. In some other places, you don't have big options. For instance, we have our receiver in Longyearbyen, close to the ESCAP, the SUSI, Svalbard radar, and there is a mountain there, but that was the only option. And we know that if we have a particular azimuth range in which we have multipath until up to 35 degrees elevation. These are all the observation above 30 degrees elevation. And see, you have seen still something. Very, very small effect. This is enhanced here because there is nothing here besides some small enhancement, some passing over threshold because of the multipath effect. And this is perfectly multipath. That's the signature. It's always the same at the same moment of the same sidereal day. We must close because we are waiting for they are waiting for lunch.
Thank you, Luca.